Hello, good morning, and welcome to the third webinar in the Next Gen Road Fuels webinar series. Thank you for joining us this morning. Today we're going to hear from Ali Sayer, who's going to talk to us about his groundbreaking research in membrane technology. In the past, the wastewater that was produced from HTL treatment wasn't thought about and then was still waste. Now, with Ali's new research, there's a possibility that this technology can turn that wastewater into something that can be reused and contributing to the environmental and economic aspects of the circular economy of HTL treatment. So it's really exciting new technology, new research that we're going to hear from Ali. So just before I pass over to Ali, just a couple of housekeeping rules. So remember to keep yourself on silent throughout the presentation. And if you do have any questions or comments, please put into the chat box. But if you do have a specific question that Ali will answer at the end of the presentation, please write in the questions and answers box, which you'll see, I think it should be at the bottom of your screen. And then we'll read those out at the end of the presentation. So without further ado, I'll pass over to Ali and we'll hear from him. Thank you very much.
Okay, thank you, Emma, very much for introducing me. Now I'm preparing my slides. Please
Perfect.
Confirm that everything is good.
Excellent. Yeah, we can hear and see everything perfectly.
Okay, thank you a lot. Then let's start. Welcome, everybody. Good day. I'm Ali Sayer, PhD candidate at Acknowledgment Institute, Water Chemistry and Water Technology in Karlsruhe Institute of Technology, Germany. I present also my institute as a partner in the Next Generation Road Fuel project, which is at a European scale. And today I would like to introduce you this presentation of 30 minutes where we will be looking for an adequate solution for treatment of hydrothermal liquefaction wastewater using a case study based on ultrafiltration and membrane distillation. So in this work, we will be using membrane technologies to improve hydrothermal liquefaction process itself by increasing the energy yield of the process, where we recover important organic compounds as well as catalysts for the hydrothermal liquefaction process itself, and hence improving the oil product. At the same time, we also produce a new product. It's an ammonia liquid, which is important and useful for fertilizers production. And also keep a note that the treatment of this waste is with zero liquid discharge condition. So no further treatment needed in wastewater treatment plants. I will start with my outline in an introduction where I will introduce shortly about how do we end up in the hydrothermal liquefaction process with this liquid byproduct. We will have briefly clarified characterization of this liquid, and we will produce the work objectives, where we start with the first treatment step of cross-flow ultrafiltration, where we recover the oil emulsions and particles back to HTL, and we produce a liquid which can go further to air gap membrane distillation, which is the second treatment part. Here, this liquid will have this step concentrating of its organic constituents and the catalysts, as well useful for HTL, and at the same time produce this colorless liquid, which is ammonia liquid, beneficiary for fertilizers production. Finally, we will end up with our conclusion. So let's start with the introduction. Hydrothermal liquefaction process usually uses biomass to produce oil, and in this work we used sewage sludge from wastewater treatment plants. Now, this sewage sludge first goes to mechanical decantation to increase the dry matter content to 23%. In addition to catalysts of sodium hydroxide and potassium carbonate, this is introduced into the hydrothermal liquefaction process at a temperature of 400 degrees and pressure of 330 bar, we will have the production of the biocrude oil. However, in addition, there are 3 different byproducts produced, which are the solid phase, the gaseous phase, and the aqueous phase, also called hydrothermal liquefaction wastewater. Now, this gaseous phase contains a significant amount of the organic carbon, as well as nitrogen, in addition to ions, minerals, and particles. So let's dig deeper into characterization of this liquid. This liquid has a pH value of 9 and electrical conductivity of 60 millisiemens per centimeter. The total suspended solids is 1 gram per liter. And of course, because of the added catalyst, we have high concentration of sodium and potassium. And last but not least, phosphate and sulfate of 2 and 1 gram per liter respectively. Now, the nitrogen is split 50-50 between ammonium nitrogen and organic nitrogen, each of 6 gram per liter. Carbon of 40 gram per liter is 1/4 in an inorganic form, and the 3/4 of 30 gram per liter is organic. The organic characterization was difficult. We were able to quantify mainly volatile fatty acids of 30% or constituting of 30% of the organic carbon. Also, there are lower concentrations of phenols, and then there's remaining constituents with lower concentrations, such as alcohols, and they also have different size ranges. For example, free surfactants in the size of 1 nanometer. We have, when they collect together to form missiles and trap oil emulsions, we can have from 10 nanometer up to higher than 100. And then finally, we have formation of colloids and particles, which can reach up to the ranges of micrometers. So treatment of this liquid is pretty complicated because of the characterization which we just saw. But let's try to make it, to simplify it and make it easier. In this scheme here, I present some of the constituents. So we can see the oil droplets in addition to some of the salts and other forms of organics. And for sure, we have the ammonia and ammonia. Now, if we perform ultrafiltration to retain the oil droplets, we will definitely produce a liquid which is free of oil droplets. And this is the called ultrafiltration permeate. Now, if this is done in a dead end mode, with time, fouling will happen on the membrane layer. And this fouling is due to the organic fouling, and of course, mainly from the oil droplets, will block the membrane surface and will not allow the permeation anymore. So to prevent this or to decrease its effect, we either use submerged membrane, which is now shown in this screen, by introducing air bubbles, which then propagate on the membrane surface, scrap the fouling layer away, and improve the permeability of the membrane. Now, since we are introducing air bubbles, we will have stripping of volatile components. This can be organic carbon, but also mainly ammonia. Now, ammonia can be recovered in several ways, such as trapping in an acid trap. This work was published in our paper last year in the Journal of Water Process Engineering. Now, the third way, and the way which we will work, which we will show in detail in this presentation, is the cross-flow ultrafiltration. Here, the feed of hydrothermal liquefaction wastewater is introduced parallel to the membrane surface in a way that the cross-flow velocity is high enough to scrap also this fouling layer. The products produced are an ultrafiltration concentrate, highly concentrated with oil emulsions and particles. And also we have the ultrafiltration permeate, which is needed for further processing. This work is published in the Journal of Membranes this year and will be a significant part of this presentation. Now, the ultrafiltration permeate moves forward and is considered as a feed for membrane distillation. Membrane distillation membranes are hydrophobic membranes. It means that they do not allow water to pass through it. However, due to heat difference between the feed and temperature, due to the difference in temperature between the feed and the coolant, only vapor would be allowed to pass through, and this can include ammonia as well as some volatile organic carbon. So we will have at the end two products, the MD condensate, highly enriched with ammonia, and the MD concentrate, which has then the rest of the salts and the main part of the organic carbon, which will then retain into hydrothermal liquefaction process as a feed to improve the energy yield. This work is published in the Journal of Separation and Purification Technology this year, and will be also a main part of this presentation, where we will use air gap membrane distillation to produce ammonia-enriched condensates. Let's start with the first part, cross-flow ultrafiltration. As we see in this illustrated figure, we will have a feed with high concentrations of particles and oil emulsions, and the cross-flow velocity used with 0.5 meter per second will scrap the fouling layer of the membrane, which is of the material titanium oxide in this work, and hence the permeate produced will have low surfactant concentration, and we will be free from particles and oils, and the concentrate will recover the rest of the oils. Now, the question is, what is the membrane pore size which need to be chosen? And here a critical point would be understanding the constituents, especially the surfactants in the liquid. So free surfactants, they can be present as free molecules in the liquid as long as the concentration does not increase the so-called critical missile concentration. However, when it's reached, these surfactants will gather all together, where the hydrophobic tail is gathered at the center and the hydrophilic heads are directed in the direction of the water, surrounding water, and will form a missile. This missile will be able to trap oil droplets and hence solubilize it in water. And missiles in general can go in the size down to 10 nanometer and up to higher than 100 nanometer sizes. So we have to make sure that what we filter produces a permeate which doesn't have particles, or which particle size distribution doesn't reach 10 nanometer. And this is what we did. We used 3 different membrane pore sizes, 30, 10, and 5 nanometer. And we saw for all that the particle size of the largest volume fraction didn't exceed 10 nanometer. Now, if we know that the permeate quality is good, we also want to know if the filtration process quality is good and if the performance of the membranes are good at the long-term basis. Hence, we have to introduce the critical flux and pressure. Shortly to define it, critical flux is the lowest permeate flux at which noticeable fouling appears. How to measure it? There's many different ways, but in our work here, we based on how the flux J changes upon the stepwise increase in the transmembrane pressure. So in the graph below, this is an example where we did it on the 5 nanometer pore size membrane. With an increase in the transmembrane pressure, the flux was increasing until reaching the critical point, where the flux is stabilized at 6 liters per meter square hour. And this happened at the transmembrane pressure of 150 millibar. So we will accept this as a limit for further experiments. We also did the same for 30 and 10 nanometer, and this is illustrated in the table to the right. The critical fluxes for 30 nanometer was 8 liter per meter square hour, for 10 is 7 liter per meter square hour. And now we adapt the critical pressures and we apply them in long-term experiments to check the permeability of each membrane. At the first glance, you might think that if a 30 nanometer membrane pore size is 3 times bigger than that of 10 nanometer, then we will have 3 times higher permeability. However, if we look at this table, this graph to the left, we can actually see that a 10 nanometer membrane has a permeability double that of 30 nanometer at a long course. So after reaching a filtered volume of 100 liter per meter square. So what happens here? To understand this, we have to look at the right, where we can see that the difference in the fouling procedure between the different pore sizes. So as we recall that missiles can go in the sizes from 10 nanometer to higher, we will have definitely significant amounts between 10 nanometer and 30 nanometer. And these can enter the pore size and they can block it. This is, however, not the case for a 10 nanometer pore size. So this is an explanation why the permeability of 10 nanometer membrane pore size is better at a long term and course. So what happens if we go down with the membrane pore size to 5 nanometer? We will see a different performance. We can see to the graph to the left that the permeability decreased in a different way. And this time it was linear, it was stable, and going down until it reached almost zero at a filtered volume of 60 liter per meter square, where the membrane actually blocked. So how does this happen? Now we look to the right and we have a look at the 5 nanometer pore size, how it was getting blocked from inside due to inner adsorption of the surfactants on the membrane, of the walls of the membrane channel from inside. So it gets narrowed with time until it gets blocked. Here we can summarize it by saying that 10 nanometer pore size is the best one due to the quality or due to the constituents of the hydrothermal liquefaction wastewater. Now we know the best pore size. What about the, and we know that in the long-term process of 1 week, it has a specific stability, but what about if we want to use it in an industrial scale for 4 months? How can we clean and how can we improve it and maintain its performance? For that, we did cleaning steps to check the efficiency of the cleaning for recovery of clean water permeability. I have to recall here that after, so we did the experiment here based on the chosen 10 nanometer membrane pore size, and at the end of the filtration procedure, we had recovery of clean water permeability of 40%. And now we want to see how much it got improved with cleaning. We started first with 3 steps of physical cleaning. They are the first, second, and third step, each for 1 hour. The first one is rising the cross-flow velocities 3 times, so up to 1.5 meter per second to believing to improve the scrapping of the fouling layer. Also increasing the temperature to 50 degrees, so that's double the initial one, and applying backwash. All of these physical methods trying to detach the fouling layer from the membrane surface. We can clearly see that the recovery didn't really increase from 40% significantly applying these physical cleaning methods. So here we move to the 4th and 5th step, which are chemical cleaning. They are done for 24 hours. And the first is alkaline cleaning with pH of 12, followed by an acid cleaning with pH of 2. Here, we can significantly see a difference. So the recovery increased up to 70%. So that's almost 30% increase in recovery by applying alkaline cleaning. In addition, there's a less increase by acid cleaning, which is here by 5% up to 75%. So we can clearly see that chemical cleaning and mainly alkaline cleaning can really improve the clean water permeability. And now let's check the permeability of the hydrothermal liquefaction wastewater based on before and after cleaning. So we compared between the virgin membrane and the cleaned membrane, and we can see that the permeability gets stabilized in long-term basis. So this confirms a good cleaning procedure. Even to the right, the products, the permeate product, also have similar quality. So the particle size of the largest volume fraction of both products from virgin membrane and clean membrane are almost similar. So now we know that membrane, that ultrafiltration, the first step, using 10 nanometer membrane pore size and cleaning chemically and mainly with alkalines, can give us a good quality permeate and can work for a long-term process in a stable state. Hence, we move to the second step, where we want to use this permeate in membrane distillation and in precise air gap membrane distillation process. The membrane used here is an expanded polytetrafluoroethylene membrane. It is a hydrophobic membrane, which, although having a pore size of 0.2 micrometer, doesn't really allow the liquid to pass through because of the hydrophobic character. So we can see in this scheme that the feed, having an elevated temperature, doesn't really pass through the pore size, but due to the temperature gradient between the feed and the coolant, you will have vapor passing through. So water vapor in addition to volatiles in the liquid, including ammonia, including other volatile organic compounds, such as some phenols, for example. Now this will pass through the membrane pores to the air gap, where it gets condensed on the polypropylene foil, and then get collected as the condensate. Now, before we proceed, we have to show a critical point related to hydrophobic membranes used in membrane distillation, which is the so-called liquid entry pressure. Brief definition is that the liquid entry pressure is the pressure required to cause membrane wetting. So whenever a membrane wets, water is able to pass through the pore size, and hence the concept from membrane distillation doesn't work anymore. To test this, we have this easy setup where we have a manometer, a pressure applied in a vessel on the membrane surface, and the outlet is checked by increasing pressure. And whenever some outlet appears, means that the liquid entry pressure is reached. We check the membrane performance with distilled water, and we reached with liquid entry pressure to higher than 2 bar, but we didn't really reach the liquid entry pressure by increasing up to higher than 2 bar. So this gives a good sign of quality of the membrane. Now, if we use this, however, with the hydrothermal liquefaction wastewater, we can see wetting without even applying any pressure. So the liquid entry pressure is 0. This liquid can in no way go to membrane distillation. However, the product of ultrafiltration, which we did before, gave us the ultrafiltration permeate, which has a very good liquid entry pressure of 1.5 bar. This is promising. This liquid can proceed and go into the second step, which is membrane distillation. So here, the membrane distillation feed is the permeate from ultrafiltration and will be called HTL wastewater UF in the scope of the work. Now, in membrane distillation, we had 6 experiments split into 2 groups. The first 4 experiments were done with recirculating the feed, where we had 4 different feed temperatures of 30, 40, 50, and 60 degrees Celsius, while the coolant temperature was kept stable at 20 degrees. The condition was recirculating, and the objective of this experiment was to check the flux stability at the long-term process, to check the permeate quality, and to know what is the optimal temperature to work with. The optimal temperature is then chosen and adapted in the final 2 experiments, number 5 and 6. And here the condition is concentrating the feed. And the objective is to check the flux at different recoveries, to know what is the maximum recovery, and finally to analyze wetting. So first of all, what is the optimal feed temperature to work with? As we earlier said, that we want to produce a liquid, a condensate, which has a high concentration of ammonia. So by assumption, we would believe that increasing temperature, as we can see here in this graph, will increase the concentration of ammonia. And the more we increase in temperature, the better we get the product. And this is also backed up with the increase of the flux J with increase in temperature, which is almost exponential. However, we have to be very careful here not to fool ourselves, because we have to check also what is the quality of the produced condensate. And this quality is defined by how much the ammonia liquid is contaminated by organic carbon. So we introduced this ammonia to TOC ratio, total organic carbon, at which we see how is the concentration of ammonia between the permeate and the feed compared to that of total organic carbon. When we look at the graph, we can clearly see that at 30 degrees feed temperature, we have a concentration of ammonia of, we have the ammonia to TOC ratio of 10. And this will increase with increasing temperature up to a value of 13 at 50 degrees feed temperature. However, this will drop slightly to 12 ammonia to TOC ratio at the temperature of 60 degrees. When we compare this also in the ammonia to phenols ratio, we also see a similar performance, increasing up to 50 and then dropping or stabilizing between 50 and 60. So here, what is happening is that between 50 and 60 feet temperatures, the rate of introduction of organic carbon to the condensate is catching up with that of ammonia, or even slightly exceeding it. As a result, this tells us that we have to stop here by increasing the temperatures, because we reached our optimal feed temperature, since we want to have a high flux, a high ammonia recovery, but also at the same time a good quality by having a high ammonia to TOC ratio of 12. After choosing the optimal feed temperature, we adapt it and we go with checking for the optimal condensate recovery. With recoveries up to 40%, as shown in this graph, we have a stable normalized flux at around 95%. After exceeding this recovery, the normalized flux drops significantly until reaching around 70% when arriving a recovery of 80%. The recovery of 80%, however, has a significant standard deviation, so it shows that it's not stable. As a result, we had to dig deep and have a look what is happening during the course of the experiment. So we saw in the first 48 hours what was happening, and it was clear that the flux was stable until the first day, so until 24 hours, and this normalized flux was at 70%. And then suddenly, when reaching 48 hours, the normalized flux increases. Now, this is a sign of wetting. This is also backed up by the color of the produced permeates. So until a 50% recovery, we can clearly see a colorless liquid, colorless condensate. But starting from 70%, we could definitely see a yellowish color, and at 80% recovery, we see a black color, which is the initial, which is the color of the feed. So signs of wetting were shown after exceeding 60% recovery. These signs are sudden increase in normalized flux, change of color, and we were also able to see permeation of other salts at 80% recovery. So all of these signs tell us that the optimal recovery is actually at 60%. So why is it limited to 60%? We have wetting, and wetting has specific mechanisms. And our investigations show that surfactants are one of the leading causes for wetting. In this graph, I just try to show the change of concentrations of different surfactants, anionic, cationic, and non-ionic, along with the increase of recovery. All of these changes are compared with a theoretical increase in concentration. If there was no interaction between the surfactants and the membrane surface, then all of these surfactants should have increased up to the theoretical increase in concentration. This is, however, not the case for none of them. And to understand what is happening, we could clearly see that there is an interaction between the surfactants and the membrane material. So the hydrophobic membrane material will attract the hydrophobic tail of the surfactant, which will then form a kind of a bridge where the hydrophilic heads will allow water to pass with time through the membrane pores, and hence leading to wetting. This definitely is related to the hydrophilic-lipophilic balance because surfactants, especially non-ionic surfactants, have relatively low HLB value. Also, there is the factor of electrostatic interaction between surfactants and the membrane material. Cationic surfactants, for example, can be attracted to the membrane surface, which has a negative charge at the high pH of 9. So the highest absorption is for non-ionic and cationic surfactants. Now let's wrap up and move to our conclusions. We can state that ultrafiltration followed by membrane distillation is a viable treatment option for hydrothermal liquefaction wastewater. Ultrafiltration membrane with a pore size of 10 nanometer is chosen as the best because it's effective in maintaining a stable permeability and giving a good permeate product. And the best cleaning procedure is alkaline cleaning, which will increase the recovery of pure water permeability to 70%. Moving to membrane distillation, we saw that a feed temperature of 60 degrees gives a good flux, high flux, and also which is also stable with time. Also, there is a high concentration of ammonium in the membrane distillation condensate of 60%, so up to 12 grams per liter, we just saw. And there is also a low organic carbon load. If we check the recovery as well, we can see that there is a limit for empty condensate recovery, which is reached to 60%, because if we exceed it, we will definitely arrive to wetting. To improve this, we can use super hydrophobic membranes, which will then be able to reach higher recoveries, and as well, we can add the membrane distillation concentrate to the ultrafiltration permeate to trap the formed missiles again after concentrating. Now, finally, I would really like to acknowledge everyone who helped in this work. This project has received funding from the European Union Horizon 2020 Research and Innovation Program. My work is a part of my PhD, a significant part of my PhD, which I was working during the last 3 years. So for that, I definitely have to thank all the colleagues in the Next Generation Road Fuel project, especially the colleagues from Aalborg University and the colleagues from Catalytic and Technology Research at KIT. But special thanks goes to my colleagues at Englabonte Institute, Water Chemistry and Water Technology, all the technicians who made this happen, the supervision, the nice and easygoing and great supervision from Dr. Ferenczi Saravia and my professor, Professor Harold Horn. And definitely the special thanks will go to the students who I supervised during these 3 years and who produced these amazing results. So Malik Youssef, Simon Merkat, and Nikhil Shailaja Prakash, many, many thanks. Thank you everybody for watching this presentation. And now I'm ready for your questions.
Thank you, Ali. That was really great. Really interesting research, and something that not many people or almost no one thinks about when we're talking about biofuels and biomass technology. So great for that insight. we've just had one question come in. It says from Christian Klomfel. Hi, Ali. Very nice presentation and impressive results. Do you have a plan for using the retinate stream?
The retentate stream. Yeah,
yes.
So that's the concentrate.
Okay, so do you have a plan for using that? That's the question.
Maybe he can explain. Okay, I can talk. We have two retentate streams, as I mentioned. One is for ultrafiltration and one is for membrane distillation. Each one of them has different characteristics, and the main scope of the work was to recover the organic carbon and the catalysts back to the hydrothermal liquefaction process as a feed. Now, the first retentate from ultrafiltration covers the main part or almost all the particles and the oil emulsions, while the retentate from membrane distillation has 80% of the organic carbon, mainly, for example, the volatile fatty acids, which are in this case as salts because of the high pH value, in addition to all of the catalysts which the HTL process need. So in this case, it's up to the colleagues working in HTL itself. Where do they want to use each of these retentates?
Okay, great, excellent. I actually have one question. Where do you see this technology going? Because you've come to the end of your PhD and the end of Next Gen Road Fuels project finishes at the end of this year. Do you have any aspirations for your technology, your research to be taken forward, or any plans?
Yeah, good. Well, let's say that at the end of these 3 years, you could clearly see that you have always fancy names of fancy technologies, but it's always related to the people who are using it, if they know how to use it. And maybe dealing with this critical liquid with all of this its complications was an example to try to understand. Membrane technology is definitely very wide and very interesting in many different fields. We just shed the light on the applicability of using membrane technology for treatment of process water in general, but in this case it was specific for HTL. And this is what we really recommend. Always try to, like there's a saying which says, give the baker half of the wheat, even if he ate half of it. So it's really like this. Try to understand, try to benefit from the engineers which you have to give you the best solution using the techniques which you have already.
Perfect, excellent. And there's no more questions from the audience, but I actually have another question that I've thought of. So before the membrane technology was thought about and the research done, what was happening to the wastewater from HTL? Where was that going?
That was a bottleneck for the work, actually. There were many thoughts of trying to treat it. There was, for example, trying to deal with it by biological treatment. However, depending, of course, on the different sources of the feed for HTL, the produced byproducts would have high toxicity. For example, presence of phenolic compounds or high concentration of ammonia. All of this is really limiting the biological treatment process, and so on and so forth. So there's really a research in this point still going until now, and there's no clear answer what to do with the aqueous-based byproduct.
Great. So really, it really is groundbreaking research that you've done. So before, as you just said, it was a real bottleneck. So great, excellent. Now, there's just one more question. Somebody's asking, presentation is good, thank you. Can I know how much maximum recovery of water can be obtained using membrane process for wastewater? So what's the maximum recovery?
Good. So, well, we had here 2 steps, right? The ultrafiltration, we did work up to a recovery of 80%.
Okay,
this
great.
This is for sure. If we could reach higher, maybe. But for membrane distillation, it was clear that using this membrane, using this configuration which we had, we reached up to 60%. Now, putting both together, this 80% from ultrafiltration and the 60% from membrane distillation, gives you around 50% total recovery. So 50% of the total amount ends up in the condensate, in the membrane distillation condensate. And of course, improvement of the recovery could be happening by further research.
Exactly. Perfect. Great. So you set it up for future researchers to continue from already a very good place of recovery of 50%. And we look forward to the future then of well, of course, all HTL technology, but of course this specific research that has come out of the Next Gen Road Fuels project. Okay, well, thank you so much today for all our participants, and a special thank you to Ali for participating and for presenting, I mean, excuse me. And I'd like to welcome all the participants to join us again for the next webinar, which will be on the 17th of May, and we're talking about the actual upgrading of the biocrude oils, which will then be used for, well, we hope to be used for road transport. So thank you so much, everyone, and see you again.
Thank you, Emma. Thank you, everybody.
Goodbye.
Goodbye.
Thank you. Bye.